Alright, this is our last video in the thermodynamics chapter. What we're going to look at here is the final connection between free energy and equilibrium. So we're going to bring back the equilibrium constant K and draw connections to that with free energy. Alright, so remember, free energy talks about how we can predict whether a process is spontaneous or thermodynamically favorable, meaning which will a process happen or will it not happen? And remember, equilibrium tells us which direction reactions will run to get to that equilibrium point. So in a sense, you've kind of have the idea that both of these are showing us which direction reactions are happening in. Okay, and we're going to draw those connections mathematically. Alright, so first of all, if you remember that at constant temperature and pressure, a system that's thermodynamically favorable will always lower its free energy. Okay, so that means that our change in free energy, as we said before, should always have a negative value to it. So that's what we're looking for, is a negative free energy. Okay, that the free energy of the system is being released or being lowered as that process happens. Now, one of the key concepts to think about here is that the equilibrium position is going to represent that lowest free energy possible. I'll go over this a little bit more in class, but it's really not worth the time and energy to spend here. I really want to get just to the stuff that's important here. But what happens is that reactions aren't going to go to completion, they're really going to go to equilibrium. You would think that if we want to lower the free energy of the system, we would want it to go completely to the products, but actually the lowest free energy is offered by the equilibrium position. So we're going to have this equation. Again, if you want to see the derivation of this equation, check out your book or check out the notes that I've written, because I'm not going to spend the time here in the videos going over the derivations. Don't forget that this symbol here is under standard conditions. So that means that our temperature is, not pressure, but standard conditions, and that means that our temperature is going to be 25 degrees Celsius, our pressure is 1 atm, and our concentrations are all 1 molar. Alright, that's what the standard degree symbol is. This is without the standard degree symbol. So if there's no degree symbol, this is any temperature, any pressure, any concentration that we want to have. We can see what the change in free energy is going to be. Alright, so R is the universal gas constant, but because we're dealing with energies, we want to use the one that has energies in it. So we want to use the one that is kilojoules per Kelvin per mole. Alright, and then temperature is obviously in the Kelvin scale because we want to connect it back to the R. And Q is the reaction quotient from the chapter on an equilibrium. Remember, it's always the products over reactants. Right, so you're going to take your concentration of products, take it to the power, and you take it over your A, which would be to the A concentration, and B to that B concentration. Remember, that's all from, we're going to look at some calculations with this a little bit later, but that's what Q is. Q is going to tell us what's going to happen. Now, think about this. If everything is under standard conditions, right, everything is standard conditions, then the concentration of C, right, concentration of C should be equal to 1. The concentration of A is equal to 1. Concentration of everything has to be equal to 1 if we're under standard conditions. So therefore, you can easily say, well, Q has to be equal to 1. Well, if we take the natural log of 1, we're going to get 0. So 0 plus the free, then these two are really equal to each other. So when everything is under standard conditions, these two things are equal to each other, and this will become the standard state condition of the reaction. Okay, so that would be what we're talking about here, is that Q is, now what if Q isn't 1? What if Q is not? So that's where these are going to start to deviate from each other, is that when Q is not 1. What if I increase the concentration of C, or if I decrease or increase the concentrations of A or B, or what if I add more pressure? Remember, you could do this all from the perspective of pressures of gases as well. Remember, QPs and all that other stuff. Anyway, that's what we're looking at, deviations from our standard conditions to non-standard conditions. Okay? All right. So let's take a look at as we go. So we know that from in the equilibrium chapter that reactions are going to proceed to the equilibrium position. So if a reaction, a Q, by the way, just so you remember, oops, it's a bad Q, but Q is just equally bad, but it's a Q, is initial conditions, right? That's when we're under initial. K is always when we are at equilibrium, right? So that's what we're referring to here is when we're not at equilibrium. So this system in this previous slide, if I go back, might be at equilibrium, but most likely it's not if we're dealing with Q. But remember, we have to do that Q and compare to K. Q is greater than K. Q is equal to K. Okay, we'll talk a little more about that again in class, but this is just some of the background information. So anyway, Reactions are going to go towards that equilibrium position. Okay, and at this point we say the reverse and the forward are equal to each other. That's how we defined it back then. Remember, we said the forward reaction is equal to the reverse reaction. Well, now in thermodynamics, we're coming back to the same point. We're defining equilibrium from a different point of view, from a thermodynamic point of view. What we do here is we're going to say that equilibrium is really defined as the position that offers the lowest free energy. And that's our definition of equilibrium from thermodynamics. And both of these two definitions of equilibrium are applicable. It just depends on which perspective you are looking at when you're defining equilibrium. All right, so this is the most important slide right here, and it's this one that has this free energy, okay, equation in it. So if we're at equilibrium, okay, the free change in G, the change in free energy, is going to be equal to 0 because we're at equilibrium, because Q is going to be equal to K. So if we're already at the equilibrium position, under standard conditions, by the way, this is all assuming that we're under standard conditions. So that means my pressure of everything is 1 atm, my temp is 25 Celsius, and my concentrations are all equal to 1 molar. Okay, that's the definition of standard conditions. So if that's the case and this drops out and we're at equilibrium, we can get rid of this because it's going to be 0 now, and we end up with K, and this is our equation for free energy. So now we can connect free energy and K together. So what this means is that if the free energy is 0, and again under standard conditions, meaning we're taking the equation K, we're plugging in our products over reactants, and if that's equal to 1, okay, meaning that everything at 1 is equal to 1, then free energy is 0. There's no free energy in the system under standard conditions. And in that case, we are at that equilibrium position, and K will be equal to 1. But remember, K isn't always equal to 1. K is most likely going to be greater than 1, or K is going to be less than 1. Remember, we talked about this before. We saw a lot of values for K. Well, under standard conditions, if K is greater than 1, then we would say that we favor the products, and the free energy would be negative. Right? Our change in free energy is going to be negative. So therefore, the reaction favors, or thermodynamically favors, the products. And we already said that K is greater than 1. There has to be more products than reactants. So therefore, both of those are pointing toward the formation of products. So we've got a couple ways to interpret a reaction and whether it's spontaneous. Free energy is 0, or I'm sorry, less than 0, right? Let's put the less than sign there. Is less than 0, or if K is greater than 1, then we would say that it favors the products. If K is less than 1, then we are favoring the reactants because we have a buildup of reactants and not products, and therefore this is going to be less than 1, and therefore the reaction would favor reactants at that point, and then our free energy would have to be positive because it's favoring that. And again, if you plug into this equation, you plug in K, whatever the sign notation of K is, going to be the opposite for the free energy. Okay, that's why these two are reverse of each other. Okay, so there's your connection between equilibrium and free energy, and we'll take a look at this more closely in class and look at some examples and finish up this unit. All right, so thanks a lot, guys.